Hello there, and welcome to LPP 3D Prints. In this video I'm going to cover Hotend and Heatbreak upgrades that apply the Neptune 3 ppm Pro Plus and Max series printers, and that will have at least some application to other model 3D printers. As there is a woefully small pool of available information about the potential that exists here, I will be covering my journey from the inception and impetus of the idea all the way through to what I believe at the current time of making this video is the peak of technology that can be adapted straight onto the existing extruder mechanism of the Neptune 3 ppm series printers. I have developed this idea such that it can be performed with little to no permanent irreversible modifications. All Neptune printers used for testing have been flashed to run Clipper. While these modifications can be done to a stock firmware Neptune, some calibration features may be unavailable. All links to the relevant bits, bobs, odds, and hotends will be in the video description. This is going to take a bit to go over, so let's get cracking. It all started when I got a printer. Not that one. This one. Yes, friend, this is no Neptune, but it does have something that the Neptune wants, and dare I say needs. Ceramic ring heating. But is it possible? Well, I began to think it might be when I started getting familiar with the Hotend of the KP3S, specifically its original model variant. Why, if only that ceramic ring was a copper or aluminum block, it would be a ringer for the Neptune 3 ppm series Hotends. And that is where the fun ends, because this little put-em there isn't worth spending much time on. While initially seeming a great drop-in replacement, same basic height as a metal block, uses V6, can use V8 nozzles, M6 threaded for various heat breaks. In taking a closer look, it can be seen that this Hotend is minimalistic to the extreme. And getting this ceramic ring heater around the M6 threaded barrel. It does the job, but with only the slimmest of edges to grip with the tool, so nozzle changes are a pain at best. This is compounded by the fact that the slim edge means that it's wrenches only, as any pliers will result in the cracking of the ceramic ring heater when they inevitably slip, and they will, first time, guaranteed, which then needs to be replaced by removing the ceramic Hotend from the unit. Couple that with a thermistor installation location that does an excellent job of reading the temp of the ceramic heater and a very poor job of determining the temp of the material of the Hotend. It is part of a 3 strikes and you're out scenario. Final word on this Hotend. If you want to work with it, go ahead. But make sure to purchase a whole bunch of replacement ceramic heater cores for it. Good to have on hand either way, but oh boy, you will break them. A lot. Best for applications with a put-in nozzle and not need to change. Also best for 0.2 to 0.25 nozzles. Slow printing speeds as temperature accuracy is questionable at best. Also, this thermistor uses an ATC Semitech 104 GT-2, while the N3 series uses the EPCOS 100K B57560G104F, while Simo, the 104, is different resistance values and will report higher temps unless the sensor type is changed in firmware. Easy to flash to Clipper, but Marlin takes recoding and reflashing or just running it at a higher speed temp as a stopgap measure. Now, thanks to Murphy's Law, we know that no good plan survives first contact, so undaunted we can continue. After all, there's plenty of good information to gain from failure. For certain, a round base mount that is M6 threaded is needed for the ceramic ring, and one existing nozzle might immediately come to mind for those who have ever looked at the various nozzle types out there today. The Volcano Nozzle. But dang, Volcano nozzles are all in metal block cores. That doesn't work. Until Creality comes along and says, hold my beer. Yes, the Volcano Nozzle was not big enough for Creality, so they made the K1 nozzle, specifically for their K1 series printers. But when you take a look here at this aftermarket Hotend for the K1, a lot of the puzzle pieces start to fall into place. Here is a Hotend kit with a ceramic ring and the same thermistor as the Neptune 3 series. That is basically a long version of the very type of part we need. Sure, that length means some things have to change, but even the Pro model of these printers can surely spare the loss of total print height in favor of faster, better quality printing. So, following the footsteps of the all-metal Hotend upgrade video, which, by the way, basically the only other actual Hotend upgrade video instructional for this printer's hot end at the time of making this, I took the CR10 bimetal Heatbreak. That is the true best stock replacement. The all-metal upgrade video would have you use one that is slightly longer and does not have the exact mark for the grub screw to lock against, and attached it in place of the Heatbreak that comes with the aftermarket kit. As with any hot end upgrade or nozzle change, it is important to make sure the nozzle and Heatbreak are tightened such that they meet securely inside the tube, leaving both room for further adjustment if they could move any further. I don't tighten it all the way down, just leave a fingernail size gap at the nozzle so you have some room when you heat up the nozzle for the final tightening before first use. Now, as these K1 nozzles are longer than the stock setup, an extension for the sensor is required. I found one and modified it to the appropriate length and added a spar for stability. It moves the stock sensor down without adding too much additional Y distance, only 0.5 millimeters or so, and keeps it nice and stable. So now, let's move on to testing and see how this upgrade goes. Note, all VFA tests shown here are the same settings, but centered to each build plate. All tests were conducted with a 0.4mm nozzle using a hardened steel or its closest available equivalent for the nozzle type being used. All tests were generated in Orca Slicer, starting at 10mm per second and proceeding up to a max of 45mm per second in the settings, with a real-world end speed of 47mm per second. The line width and height are at a max a 0.4mm should be able to output mathematically, being 0.7mm width and 0.32mm height respectively. The material used is Sunlu PLA Plus Sunny Orange. All nozzle flow rates were verified to print dimensionally accurate at a flow rate value of 100%, or 1 depending on how it's entered in your slicer, with a 0 to plus 2% margin of error. Flow calibration was performed using the test model and parameters specified at the site in the description. Flow calibration was performed at 235 degrees C, while VFA testing was performed at 240 degrees C to allow for best potential performance during testing. There was one variable left unaccounted for fully in testing that will be called out as the test results come up, and which will be fully explained in the conclusion. This variable would have contributed to the test results showing less than full performance than may be capable from the given nozzle being tested. Variable notwithstanding, I still stand by the results to follow. Now, to be as short and sweet as possible, this worked great. Here we can see the results for the K1 nozzle using the stock size CR10 Heatbreak, which was able to reach up to 30 to 32 millimeters per second before starting under extrusion and suffer layer adhesion issues. Let's get a ruler on that so you can judge for yourself. I did have the idea of using the V6 smooth style Heatbreak to be shorter, but this needed two 7mm outer diameter, 4mm internal diameter aluminum spacers to put it at the correct height and keep the heat away from the PTFE tube, and still produced subpar results compared to the stock size bimetal Heatbreak. The results from this one were still beating the stock hot end configuration, but not great compared to the stock. Basically similar, reaching around 25mm per second before immediately starting to under extrude and have severe layer adhesion issues. The subpar performance may be down to the one variable left in this test. At this time, I also placed a Volcano CHT nozzle in place of the K1, making the necessary adjustments to the hot end screw depth so that it was properly secure. Here, the results were even more disappointing than the short V6 Heatbreak, managing a meager 20mm per second before severe flow and layer adhesion issues occurred. Once again, the variable is potentially in play here as well. So here it is that I come to the end of my story. Or so it would be had there not been another Creality nozzle that was in and amongst the K1 hot end upgrades. Yes, friend, Creality makes not one, but two hot nozzle upgrades for the K1 series printer, and this is the magic sauce, the missing link, the key to the very kingdom itself. I am, of course, talking about none other than the Creality Unicorn Quick Swap Nozzle. Yes, you heard me right. Your Neptune 3 ppm series printers with just a few modifications can fit and run an easily removable high-efficiency nozzle. It even uses the same EPCOS 100K thermistor as the Neptunes run. It is no exaggeration to say that this basically doubles the flow rate compared to the N3 stock Hotend. But as they say, seeing is believing, so let's get to the test results. And here it is. And right off the bat, the differences are starkly apparent. Of all the nozzles and configurations that have been tested, the Unicorn nozzle is the only nozzle that has been able to fully complete the VFA test print, all the way up and through the 45mm top set speed. Here is some B-roll of the test being printed. I mean, just look at that visualizer go. Whew. Aside from the successful completion, we can see acceptable extrusion up to around 30 to 32 millimeters per second. But even after that, while slightly under extruding, layer adhesion was not suffering. This means that if you can accept such results in a non-visible environment, a faster infill print could be used to reduce print time without sacrificing quality in hidden areas. Cool, yeah, awesome, right? But how? Well, there are two crucial pieces to this upgrade. The first crucial piece that makes this all work is actually an aluminum tube of appropriate size. 7mm outer diameter, 5mm internal diameter. However, due to the properties of aluminum, they do need a bunch of hand working over before they will properly fit, immediately become stuck and lodged in the heatsink. So, in an effort to make this upgrade available to the community at large as easily as possible, I will be selling pre-cut, worked, and drilled spacers that are tested, ready to go, and easily removable. You'll be able to grab one at my Etsy store linked in the description. If you decide to source and cut the tube yourself, make sure to use proper protective equipment for the job, like proper eye protection and a quality breathing filter like a P100 rated mask, as aluminum dust is toxic and you will be making a lot of it. The second crucial piece is actually the variable that has been hinted at previously and has been sitting in view the whole time. This is actually the thermal paste known as boron nitride. You need this. You will not be able to achieve the same results without it. I say that as all testing that did not properly utilize this or did not have it properly applied had subpar results compared to the same testing with the boron nitride applied. The reason it was called out as a variable in the testing is because while all heat breaks had it applied at the heat break to heatsink connection, it was not until the Unicorn testing that it was applied to the threads of the nozzle. This is due to how the Unicorn works and is installed as you insert the whole nozzle through the Hotend. But in coupling with Creality's official nozzle kit, it exemplifies why it is necessary. Here, you can see the official Creality kit has a freely rotating ceramic ring indicating little or no thermal paste material between the brass and heater core, leading to poor heat transfer. Results with the Creality core kit are all garbage, regardless of whether I use the official Creality nozzle or an aftermarket one. Final note on the official Creality kit, I did reach out to them regarding the freely rotating ring and the concerns regarding inefficient heat transfer. While I will not post the full email, short though it was, I will summarize. They state the ring freely moving is as intended for user positioning, and believe that some thermal mating material may be beneath the heater core. However, as their writing indicated, they could not consider or conceive of any scenario that fell outside their own print devices. All additional statements beyond that do not apply to this project. To finalize why boron nitride is so important, please allow me to TLDR the datasheet info about boron nitride in a garbage manner. Basically, microscopically, it's hexagons. It's hexagons all the way down. This means they're able to slide and interlock very well on a microscopic level in both single and multi-layer configurations. When you heat them, this then locks the structure into place, effectively making a solid thermal transition layer whose thermal transition properties actually improve the thinner the application layer is. Yep, the thinner it gets spread out, the better it transfers the heat. This makes it perfect for being in the spaces between the nozzle threads as well as between the brass core and the heater core. And that then goes the same for the spacer in the heatsink. Even though the work spacers are somewhat rough, the boron nitride will fill all the spaces perfectly. Final word of warning. You might find brass tubes of the same dimensions. Do not use them. This chart shows the thermal conductivity of the metals we use in 3D printing hot-end systems and nozzles, and as you can see, brass is second only to steel in poor thermal conductivity. Copper is king here. But going then into brass, then back to aluminum, will leave too much heat sitting in the Heatbreak instead of being wicked off to the heatsink, and results are not expected to be as good. I have done no testing in this area. Alright, now you are armed with the understanding of how this works. Now is the time for making it work. I will take you through the process from start to finish, covering all aspects and noting what is potentially optional. The full method involves complete toolhead disassembly, but if you only want the quick version, you can do your install following along from that point. Either way, it is recommended you watch the full process first and then decide. Additionally, it is recommended to print out the STL for the new cooling fan system before doing any modifications. Stock cooling is untested, but while stock-sized cooling will work a bit, it is nowhere near optimal and will potentially make printing the new nozzle cooling system more difficult until a correctly positioned cooling system can be installed. My preferred cooling option will be bundled in the link with the sensor extension, while an alternative that also works with the sensor extension will also be linked in the description. My preference includes the function for use of an endoscope. The optional one is more freeform. We will start from the point of the tool head being removed from the printer and ready to be worked on. Please be advised, your outer shell may look different due to being stock or modified already, but all screw locations should be the same. We will remove the backplate, fans, casing, and extruder motor so we can gain direct access to the initial filament tube infeed area. This is also a good time to clear any debris from the tool head. Let's go ahead and crack in here. So we're going to get these, first get our faceplate off. And then get our alignment mount for the cable and back plate off. Get all our fans out of the way. Pliers are really, tweezers, thick tweezers are really handy for this. All right. Out comes this fan. Oh, see? Really don't want to do that with your fingers. Oh, it's going to do the thing. Yep, don't worry if this happens. You can just carefully... I'm going to need better pliers. 1 sec, please. Get that out. Carefully lay this back on. Flat, and then push it back on. Good to go. As long as you don't bend those pins, fairly easy. Avoid this screw here. This is your tension screw. You'll get more of that visibility in just a second. All right. What we want is right back here. So the next step, yep, is going to be taking off this. Honestly, I forget if this board needs to be removed, so we'll take a look underneath that as well. I don't think so. I think it unscrews the other way, but... Oh, nope, I was wrong. There's our screws. Okay. So once we have access to all this, Don't mind the fact I already have it installed. We'll be going over that with its removal shortly. Oh, I might actually need to take it off now. There we go. Look at that. Careful with these. These are removable. Do not lose them. I lost one of mine. I'm going to have to replace that with some other screws there, and that'll pop right off. Now we're down to, remember this one in the corner here is going to be the non-flat. There's our heat block. You can see I already have the spacer installed. I don't want to rip that one out since it's already nice, good thermal mating. So I'll take one of the new ones here and just give you a quick demonstration. Pops right in, and there's a little hole where you can use one of these bent hook tubes and work it right back out if you need to, or push it in if you have this completely removed to pull it out. But with that little hole, you don't actually need to do this full disassembly in order to have what we want. Now there is a reason for this, and you will be needing a few extra pieces, which we will go over now that we have this disassembled. And the two pieces carefully separated, we can take a piece with the filament tube. I know I have some here already. Oh, where'd she go? Here you go. And insert that. And cut that to length. For this, you're going to want a section of 4mm outer diameter, 3mm internal diameter Bowden tube. Not to be confused, the 2mm internal diameter that you may see. The 3mm is what you want. You'll cut this to length of this plastic shaft. And then you can use any old nozzle here. This is really nice. Just, we want to flare the edge of that. So we want it to stick out even larger, so that when this PTFE tube is inserted here, it's not going to go down this hole here. This PTFE tube will act as a retaining ring, helping to increase tension on the nozzle so that it does not unscrew itself and drop down, which all nozzles have the potential to do, and I have dealt with in the past. The stock Creality Unicorn kit, she must be tight, has a tiny ring for this same purpose. And I have been printing without this in place currently and have no real issues yet, but I'd rather have the tube here, as the nozzle does feel very easy to move if it's not. The tension of the nozzle inserted in the tube will act as a retaining ring, just like came with the kit, helping to prevent the nozzle from backing out. Better safe than sorry. Here you can see how the nozzle will interact with the tube and how we want it to stay caught above the heatsink. So I thought this was long enough, cut this to length, and I will flare that edge appropriately. There we go. And back to the flare. Any nozzle will do. These K1s being long enough will help. If you've got the Unicorn on hand, it will perfectly work. MK8 nozzle will certainly do the job. There you go. So let's get that tube in there and make sure it sits as flush as possible. We can even use our heatsink to help smudge her down there just a bit more. And then you can see that's very tight, but the tube is now held in there. Again, pushing this out, picking this out, this is fairly easy to remove. It can also just get stuck on this once it heats up. So, now, assembly is the reverse of disassembly. Gotta love that. It's going to go in this orientation with the fatter side towards all your notches here. This is where you're going to clean out. This is your adjustment ring for how tight this is going to grip the filament. You don't really need to mess with that. You do need to make sure that this here fits back into this O-ring here, and you can also, if you feel so inclined, apply additional grease. At this time, also this spacer here needs to go into this hole here so that it will have leverage once more. That's unnecessary at the current time. In order to achieve this, you may have to, see, she'll get away from you. You have to hold back on the lever somewhat so that this is more freely moving and can go back to its home. There you go. And then once it's seated, you're good. Just hold the tension on there. Get some of your top screws. Lock it back down. Oh, right, that goes into the motor. Yes. This one is your lock screw, the rest ones are motor screws. This is fairly straightforward. This motor cable goes on the right side from the front, left from the back. And we slip in our motor retaining screws. Make sure you got rotation. And now we can put our board back. Making sure to align all holes. Whoop, don't get caught there. This fan goes there, the cooling fans go there. And then we want, not this, yes, that, in a minute. Okay, there she goes. And that's good enough for I'm going to do this. Okay. Get that centered there. Now, mostly back together here. And this is where the short method begins. Or if you have been following along now, this is the part where we will adapt the hot end to the existing mechanism. Again, there are two ways you can go here as well. The first way is that I will be demonstrating is to make another hole in the heatsink using a tiny 1.8mm drill bit, or number 50 to 48 if you have a full drill bit set. This is the method you must use if you are still using Marlin firmware. This will allow the nozzle to sit centered with both screws secured, so that the nozzle position is the same X and Y distance from the sensor as the stock hot end would be. The second way is to simply leave this inserted, with only one screw. This will allow the nozzle to center on the heat break hole with the spacer, but you'll still need to remeasure the X and Y distance to the center, as it will have shifted with the angle of this turn. Additionally, the nozzle tilt may occur with only one screw to hold the nozzle level, so a second screw hole is the recommended way to go. To start, get this back out and get my demo here. I put in the wrong one. That's funny. Well, whole thing it is. Start. Coat the spacer with a quick coat of boron nitride. Since once installed here, we do not need to remove it. This is a great place to make use of any purge lines. Here's one. Get it here. There's your spacer. And there's your paste. Oh! You see exactly what I was trying not to do? Perfect. A toothpick or twist tie works equally well. Once coated, insert fully and wipe away the excess. Clean up. No worries about getting it on you, it's not toxic to touch. But clean up properly or wear gloves if you prefer anyway. Next, use this in place because it's got good centering, but screw in your aftermarket unicorn or stock Creality unicorn, both will be great, into the heat break. Yeah, I don't recommend the kit. Official nozzles? Yeah. Official upgrade kit? No. All because of, well, the fact that I discussed earlier with this. Do get the aftermarket upgrade unicorn kit, as it's going to come with the same spacers that are used, just like this. But most importantly, the top of the Hotend is a reverse screw cap. So it can be removed and you can change the ceramic core if it breaks, or apply additional thermal paste as necessary. The Creality is a press-on cap, and as stated before, the ceramic core hangs loose and makes very poor thermal contact with the brass core, so it's basically useless. That being said, if you do follow my advice, make sure to get some spare heater cores as well, since the aftermarket version may come with a short cable that is too short to reach the connection. The replacement heater cores are sized to a less custom length and reach without that issue. Once the nozzle is in place, put one screw in loosely. There she is. Oh, there it is. And center the nozzle. Now, using a hand drill, .8. Where'd it go? Dang it. There you go. Do I need the other core? Right. I don't want to fit any of these. Come on. That ain't it. There it goes. Alright, now, using this hand drill, just going to mark okay, not this hand drill. Using the hand drill, gonna make a mark best we can here. And do that as necessary until you can remove this. And see where to drill. Next, and this takes a bit, drill in carefully by hand, at least to get started. You can switch to a drill at this point or finish by hand. You only need to get down about 1 fin's depth. So I'm going to take a break while I drill this, and we will rejoin. Alright, now that we've got our hole drilled, we can take our M2 screw, carefully insert it into the hole. As long as you didn't do this too deep, you should be good. On mine, I think I've done it too deep. Insert it in. You're going to push down with your Allen key and just get it to bite and slowly create the threads that will hold it in place. If you drill too far, the fatter part of the back of the drill bit may start to get in the hole, or you may wobble too much, which is why I only recommend going down 1 fin's worth. You don't need that long a screw from your M2 screw set. So with our pieces here, we're going to insert that. We're going to lock our screw into place. Mine, from other sections of the testing, has had more modification done to this piece here than yours will come from the factory, so there'll be less variance to yours. Lock that down. Now we can remove our nozzle since we have it aligned. Well, You know what? Keep that section in there. Let's put in our new screw. So we've got our M2 set. I'm going to use a lot of washers here to actually make up for some missing pieces that I have lost through the testing process. We can get our screw. Oh, yeah, watch you don't drop into the fan. It likes to do that if you lose a hold of it. Too short. So that's M210. Nope. No, it's M28, so let's do a 10. Ten will work if you've done the hole correctly. If you haven't, like me, you'll need to mess with your choice of screw length until you find one that bites appropriately. There we go. Oh, no, see? The spacers are there for a reason. Pulling the nozzle over. Knocking out of alignment. I need to use washers to fix that up. But let's finish off. So, we can take our boron nitride here and apply to the end of our heat break section on this hot end. And you'll see here in a moment why the boron nitride suddenly became a discovery, because no matter how you do this, when you insert this, it's going to coat onto those threads. And the best you can do is just roll forward and insert the nozzle until it just simply cannot be turned anymore, and at that point, clean up. Do your best to wipe out the globs that are around the end of the heat break here. We don't want any globs in here where we can help it, since that's going to mess with some of the air path. So as much as we can, we want to wipe that out. Once cleaned up, connect the printhead cable back to the printhead, leaving it on the build plate. You can now power the printer up and heat the hot end. No movement needed. Once hot, grip the nozzle base with pliers or a wrench and tighten down the nozzle. Be advised, with the aftermarket nozzle core, the black part will begin to rotate once you've fully tightened it, and loosen if the nozzle is tightened without any counter rotation from the pliers or wrench. It's reverse threaded. Once tight, turn off the heat, install the HeatSoak, and reinstall the printhead. Once the printhead is reinstalled, you need to make sure you do a PID tune on the hot end. Instructions for this are linked in the description if you are unfamiliar. If you run Marlin, you may need to update to the latest firmware version to enable this functionality, the M303 command. After that, make sure to recalibrate the Z offset and get your first layer level correct. Then move on to calibrating flow again. This is where you should be pleasantly surprised. As the Hotend is now quite thoroughly melting the filament, you should be able to use a flow of 100% or 1 and have near perfect dimensional accuracy, assuming you have already performed skew correction on your printer. Logically, this should also translate into better layer adhesion at lower temperatures, which is good as you will likely notice more leaking from the nozzle as it gets to temp at the beginning of prints. It is also worth noting that, in my opinion, I am experiencing much better first layer adhesion application using these nozzles even. That is to say, less tags, little to no pull-up on material if it was getting put down, and seemingly a better ability to lay out more complex patterns and moves than previously able to do with consistency. Not that it couldn't before, but when it's 0 to 1 retries to get the first layer down with the small motions, complex shapes versus 5 to 6 retries, you can get the sense that things are working better and the first layer is more trustworthy. And so there you have it. One unicorn nozzle installed. Whether you use the official Creality nozzle, which I recommend you do, the nozzles, not the kit, on this setup or run an aftermarket clone, both should perform for you. In testing, the official Creality nozzle had the best performance, but the aftermarket was near as makes no difference. Basically the same. Either way you go, both will have exceptional performance once installed. It is my hope that the spacer I am offering helps turn this from a work, test, rework project into what should be a fairly simple drop-in replacement. If you found the video to be helpful or useful, please give a like and help increase visibility for others. Also, if you know anyone else who uses a Neptune 3 ppm series printer, let them know about this video, and help them come out of the dark ages too. Otherwise, that's all I have for now. Take care and happy printing!